Hello and welcome once again to our lecture on complex analysis, and in our continued discussion we'll start from analytic functions. Now the notion of analytic functions is fundamental to the discussion of differentiation of complex valued functions. So recall that a complex valued function w is equal to f of z can be written in the form u of xy plus iv of xy. And so, in order to fully discuss analytic functions, we need to know both the Cauchy-Riemann equations. And now, recall that we have said that Cauchy-Riemann equations are these relations. So these are partial derivatives. Fine. So these Cauchy-Riemann equations give us a necessary condition for a complex valued function to be analytic. And now the sufficient condition is that these partial derivatives must be continuous. And so we'll say that then that a complex valued function f of z is analytic if and only if the Cauchy-Riemann equations are satisfied, and number two, if these partial derivatives are continuous. Now these are the Cauchy-Riemann equations in rectangular case, and I did at one point I did give you an exercise to try write down these equations in polar form. And the polar form looks something like this. The partial with respect to theta is equal to r, the partial with respect to r, and then the partial of v with respect to theta is equal to negative r, the partial of u with respect to r. And I believe that you saw how this came about. You can open it on the textbook and see the derivation. So now, as an example, let us see what happens for this function f of z is equal to the conjugate of z. And so we want to check whether this function is analytic, and if it is analytic, perhaps try to figure out the region in which it is analytic. So this function can be written in the form, so if you take z to be x plus iy, then this can be written as x minus iy, so that this is the real part and this is the imaginary part. And so so we notice that u of xy in this case is x, and v of xy in this case is the negative of y. So let's calculate the partial derivatives. So the first partial with respect to x is equal to 1. The first partial with respect to y is 0. So that is for u. Then you can also consider the first partial of v with respect to x, and that is 0. And the first partial of v with respect to y, and this gives us negative 1. And so let us check for the Cauchy-Riemann equations. We require that the first partial of v with respect to x to be the same as the first partial of v with respect to y, and we see that that is not the case. And so this function is not analytic anywhere, and that is since the first partial of v with respect to x is not the same as the first partial of v with respect to y. But now maybe we can just say that since the Cauchy-Riemann equations or the Cauchy-Riemann equations are not satisfied, or one of the Cauchy-Riemann equations is not satisfied. So in the next example, I want to discuss the analyticity of this function. And so again, in order to discuss the analyticity of this function, we simply need to first of all check that the Cauchy-Riemann equations are satisfied and that the partial derivatives are continuous. But now we are going to do this in cases, because this part here is rational and this part is also rational. Then we need to check that the denominator does not go to 0. So the cases that we could possibly have, so we can divide the entire complex plane into these 4 quadrants mod the axis. So we can think of the case where x is not equal to 0 and y is not equal to 0. Because you know that something will definitely go wrong when x is 0 and y is 0. When x is 0 and y is 0, this function is not defined. So we can say not defined when x and y simultaneously as both 0. And so the first case we are going to look at is a case when x is not 0 and y is not 0, and probably consider the case when either x or y is 0 to check what happens on the axis. And so for x, y, or rather, when we are not at the origin, let's now start by taking the first partial. So we know that this is u of xy is this function here. So the first partial of u with respect to x will be the derivative of this with respect to x, which is 1, plus the derivative of this with respect to x. And for this we need to use the quotient rule. So first of all, we'll differentiate the numerator, get 1, then multiply by the denominator. Then after that we subtract the derivative of the denominator with respect to x. So that gives us 2x. Then we multiply by the numerator and then divide by the square of the denominator. And so if you work this out, you should get 1 minus x squared minus y squared over x squared plus y squared, the whole quantity squared. Next, we find the partial of u with respect to y. So the derivative of this first part will give us 0. Then the derivative of this part, again we use the quotient rule, but now this is much more like the reciprocal rule because x is a constant. So we'll get the negative of the derivative of the denominator. So that is twice y multiplied by x. Then this is over x squared plus y squared, and this whole quantity is squared. So let's also look at the first partial of v with respect to x. So once again, this will be 0 minus the derivative of this part. So again, with respect to x, this acts as a constant, so we can make use of the quotient rule, and so we'll multiply y by, we'll have the negative of 2x, and this whole quantity we divide by x squared plus y squared. And so this gives us twice xy over x squared plus y squared, the whole quantity squared. And then finally, we find the first partial of v with respect to y. Now, the derivative of this first term will be 0, sorry, will be 1. Then the derivative of this second part is by quotient rule. So first we differentiate the numerator, leave the denominator constant. Then we subtract the derivative of the denominator multiplied by the numerator, and this we put over the square of the denominator. Once again, if you work out this keenly, you will get 1 minus x squared minus y squared, and this is over x squared plus y squared, the whole quantity squared. And so if we, by the Cauchy-Riemann equations require that the first partial of v with respect to x to be the same as the first partial of v with respect to y, and we notice that these two are equal. And then again we require that the first partial of v, pardon me for this, if we, so now here this was meant to be a negative, and that is because when we differentiate this part with respect to x, we get, sorry, with respect to y, we get 0. We differentiate this part with respect to y, again we use the reciprocal rule, which requires us to take the negative of the derivative of the denominator, which is a negative of 2y. We multiply by the numerator, which is x, then divide by the square of the denominator. So that this negative should be there. So this is the right derivative. And so as you can see, the partial of u with respect to y is negative of the partial of u with respect to x, and so this function is I mean the Cauchy-Riemann equations are satisfied. Then we also need to check that these partial derivatives are continuous, and as you can see, whenever we are away from the origin, then all these functions are defined. And again, if you work out the limits, then the limiting value will be the same as the functional value, and so all these functions are continuous. And so when we are, as long as we are away from the origin, this function will be analytic. And so I leave it to you to check what happens when say x is equal to 0 and y is not equal to 0. That will be the second case, and the third case will be when x is not equal to 0 but y is equal to 0. Just try do the same thing. In this first case, try replace x with 0 and see what happens. Check whether the Cauchy-Riemann equations are still satisfied, and also check whether the partial derivatives are continuous.